as I told you, we will be talking about the physical oceanography. And the main textbook, what is available on the web, is the Introduction to Physical Oceanography, which is by R.H. Stewart, Texas A&M University. You will, you can find it. I think I gave you. Yes, this is the link, and I will be trying to base my lectures on this book. Although I'm not very, I can think of a better book, but unfortunately, so far I haven't prepared any textbook myself. I'm a little bit lazy for that, and but you will find almost everything there. Whatever you have, whatever problem you have, or whatever questions you have, you just ask me. I'll try to give you some additional reading material. So the physical oceanography. Let's see what is it. But before, I would like to tell you a few words about course syllabus. There was a big stick here. There is a?
Yeah.
Ah, yes. Yes. Everything changed. This stick was there, you know. So, this is the course syllabus, and we will see this historical and physical settings, atmospheric influence, oceanic heat budget and water budget, so that means the energy consideration of the ocean. Then we will be talking about the state variables of the ocean, which is temperature, salinity, and density. These are the variables which determine the state of the sea. And we will talk about the spatial distribution over the world ocean of these state variables, which is very important, because then, from the basis of the state variable distribution, the equations, the motions in the ocean appears, try to smooth down the differences between different parts of the ocean. And then, so we come to the third part, which is the motion of the ocean, and some consideration of the equations of motion with and without friction. With and without friction, because friction to a certain extent complicates the life in the ocean, but we have to take into consideration friction, otherwise we cannot describe in a satisfactory way the motions in the ocean. We have the response to the wind of the then we have something which is called geostrophic currents. Those who are working, who have some experience in meteorology, know that the geostrophic wind is a specific solution of the equations of motion. And so equivalent to geostrophic wind, we have a geostrophic currents in the ocean. Then we have wind-driven circulation, which is another very important part of the circulation. We have the vorticity. We'll be talking about the vorticity of the ocean with torque, because we are sitting on the rotating Earth, so the vorticity plays a very important role. We have a deep circulation because the ocean, major part of the ocean, you will see later, is deeper than a few hundred meters, so it's very important to know the deep circulation. We have ocean waves, which I will not talk about that too much. I will be mentioning the long waves, but not the short wind waves. Then we have coastal processes and tides, and I'll be mentioning just the Venice Lagoon example. Have you been in Venice? Okay. Lagrangian observation. Then we have the last part will be the observations in the ocean and the methods of measurements in the ocean, the currents, the temperature, the salinity, and all this stuff. And we will be talking about the remote sensing that means satellite observations, or land-based remote sensing. And then we will be talking about the in-situ observation, the observations which has been taken, which in the ocean, you have to put your instrument in the ocean, not from a remote site. So this is more or less the topic we will be addressing within these next 5, 6, 7, 8, I don't know how many weeks. You will be sick of myself. And so this is course syllabus. And now we can start with the introductory part. Introductory part I will try to introduce to you the general characteristics of the ocean, and so the basis of our understanding of physics of the ocean. We have what are the physical properties of seawater. The physical properties of seawater, as I told you before, here are the state variables which gives the physical properties. Not only we can talk about also the transparency, optical properties of the ocean, which are another component of the physical properties of the seawater. Then we'll be talking a little bit what are the important thermodynamic and dynamic processes influencing the ocean, because thermodynamic, which is associated to the heat, and dynamic processes, which are what are the forces which are determining the flow, which are determining the motion in the ocean. What equations describe these processes? We try always to put down the equations in order to be able to describe these processes. So the same thing happens with the ocean. We set up the series of equations which describe the motions of the ocean, and what approximations were used in the derivations. Because if you put all the equations which we would like to describe completely the motion, for example, in the ocean, the equations are very complicated, and not always we can find the solutions, analytical solutions. So what we do the simplifications, approximation, in order to get the simplified solutions, which are at the same time realistic, because it doesn't make any sense to find a simplified solution which are not realistic. Do the equations have a useful solution? This is something similar. How well do the solution describe the processes? That is, what is the experimental basis for the theories? This is more or less the same question as I told you before. The simplified solution has, to a certain extent, describe the process. Otherwise, it's not of any use. And then, what is the experimental basis for the theories? Which processes are poorly understood, which are well understood? This is another thing. When we study the ocean, we would like to concentrate ourselves to processes which are poorly understood. The processes which are well understood, they are not in the first priority. What are the sources of information about the physical processes? Well, physical variables. Here we come to the measurements, to the experimental studies. So here are the questions what we will be addressing later on. What instruments are used for measurement each variable? If we are talking about the temperature, what kind of instruments we are using? Obviously, the response is thermometer. But what kind of thermometer we are using for the continuous measurements, for the instantaneous measurements, for registration of the temperature, and so forth? What are their accuracy and limitations? This is another very important thing, because accuracy and limitation limitations are essential in deciding what kind of instrument I'm going to use. If I'm going to use if I would like to measure the sea level variations, okay, and I know that the sea level variations are on the order of of a meter, I don't need in that case the accuracy of 1 millimeter, okay? Or vice versa. If I'm measuring the sea level oscillations on the order of a millimeter, I cannot measure with an instrument which has an accuracy of a meter, right? So all these things has to be addressed before decide what to do. What historic data exist? You don't when you study oceanographic features, you don't really go as if you started with a zero. You always have to go to the literature. You have to go to the historical data available and use these data in order to find out at which level did our knowledge arrive at that specific area. And then from that you start. So in order to do that, you use the historical data and then do the measurements, additional measurements. What platforms are used? What kind of techniques we use for the measurements? We can use satellites, ships, drifters, moorings. Satellites are measuring this remote sensing, those remote sensing data, remote sensing measurements. Ships, when you use ships, that is in situ measurements. You have to put something from the ship into the sea. Drifters are those instruments which are moving following the currents. So the currents are taking wherever it wants your instrument, and then it measures along the current flow. So these are drifters. We call it also Lagrangian measurements, which is following the measurements following the current. And then we have, yes?
Is Argo float one of them? Is Argo float an example?
Yes, that's right. That's right. Yeah, we'll be talking about Argo floats a lot. Then we have moorings. Moorings, that means that we anchor our instruments at a certain point, and it stays there. It doesn't move. So, with respect to these drifters or floats, which are following the currents, we have the fixed point where we do measurements with the mooring. So we anchor the mooring and our instruments, and they stay there. So we have, this is the Lagrangian measurements, and this is called Eulerian measurements. So measurements at a point or measurements following the currents. Obviously, Lagrangian measurements, you will see later, can be used in order to describe Eulerian type of the flow. So that means if you have the large number of these drifters which are going away around, then you can have like a simulation of the Eulerian measurements at different points. So you describe your flow with Lagrangian measurements as if you were using the Eulerian measurements. But we will be talking about that later, don't worry. If you have any questions, you just interrupt me and ask. I will not be angry. I will just leave the room. Okay. No, seriously. Talking, you just interrupt me and ask. What processes are important? Some important processes we will be studying are heat storage and transport in the ocean. The heat is stored in the ocean, and you will see later that the ocean has a large heat capacity. So having a large heat capacity, that means that the capacity that keeps the heat, which once it absorbs, much more efficiently than the land, for example. Because the land has a lower heat capacity, and this is why, for example, we have a much milder climate near the ocean, because the ocean smooths down this difference between summer and winter, for example, because it keeps heat, which has which puts in it during the summertime, and it has a larger memory in a certain sense of the heat with respect to the land. So this is why we have a much milder climate where we are close to the ocean. And the heat storage is obviously different to different parts of the ocean, different latitudes, because the main heat comes from the sun. Therefore, there is a different heat content in different parts of the ocean, depending simply on the latitude, simply on where you are with respect to the sun. And so the transport of the heat in the ocean and the currents which are responsible for the transport, they try to smooth down these differences between north polar areas and the equatorial areas, for example. So the heat transport in the ocean is extremely important because it smooths down these differences between polar areas and the equatorial areas. Otherwise, you will be having the continuous heat content increase in the equatorial areas and heat content decrease in the polar areas. But this is not the case, because there are currents which are trying to keep these differences constant. Okay? And heat exchange of the exchange of heat with the atmosphere and the role of the ocean in climate. This is another very important topic, especially now when we are facing the climate change problem, and in general, but not only in the climate change problem, but also in general, ocean plays an important role in the climate. And one of the simple example is what I just mentioned a few minutes ago: is the when you live close to the ocean, you will see that the climate is much milder than if you are in the continent. You will see that there are much bigger difference between summer and winter in the continent, between day and night. And so the ocean obviously plays an important role in the climate, simply because of this larger heat capacity. Then we have a wind and thermal forcing at the surface mixed layer. Wind is a mechanical forcing, obviously, because there is a difference of velocity between the air and the ocean. So you have the heat, the momentum transfer from the air into the ocean. So the ocean tries to move to the sea because it simply has a larger velocity. You know, you meteorologists know, but all of you probably knows that the ocean, the wind has a typical speed of 10 meters per second. Okay, typical, right? And while the typical speed of the currents is 10 centimeters per second. So we are talking about the order of magnitude smaller speeds in the ocean than in the atmosphere. That means that the atmosphere pushes the surface layer of the ocean and gives the momentum to the surface layer of the ocean. And this is why we have this. We are talking about the mechanical forcing. And then we have also the thermal forcing, which is due to the air-sea heat exchange, due to the absorption of the heat from the ocean. And the last thing is the wind-driven circulation, which is due to this wind mechanical forcing. And so we call this this is the Ekman circulation, Ekman pumping. We will be discussing about this much more Ekman is a guy who in early last century, in early years of last century, has developed a theory of the response of the ocean to the wind's forcing, getting the analytical solutions, simplifying the equations of motion, getting the analytical solution of the ocean. Then we will be pumping of the deeper circulation and upwelling. You know what is upwelling? Yes, you know that upwelling is upward motion of the water masses from deeper layers into the surface, which is generally due to the wind influence. We'll be seeing later how the wind can pump the water from deeper layers into the surface, or how it can suck the deeper water into the surface. But we will be talking about this later on. Okay, so this is the just historical setting, few points on how the oceanography has developed, and yeah, I won't go to all these writings. But the very beginning of the oceanography was in the 17th century, and then you see the number of events in the ocean, in the oceanography, in the development of the oceanography. For example, you see that at the end of the 19th century there was the first expedition of in situ measurements, ship in situ measurements in the ocean. So this is the late 19th century. So this is those are the beginnings of the experimental data. Early 20th century, Bjerknes published Dynamic Meteorology and Hydrography. You probably have heard from him. The biggest oceanographic institute, Woods Hole, has been founded in 1930. For example, the most important theory evolution of the wind-driven circulation in the ocean is from the mid-19th century, 20th century. This is 20th century. Then we have theory of the deep circulation in the ocean is 1958 by Stommel. Here is the one more important stuff is the beginning of the remote sensing. So this is the NASA launch is the first oceanographic satellite CSAT, and this is the first remote sensing satellite, the first of the remote sensing satellite family in oceanography. What else? Here is the first in 1992 the first autonomous drifter have been used for the oceanographic study. So these are the Lagrangian measurements. So you can see that this is a pretty recent studies. In 1993, this is another very important point of the development of oceanography, and the remote sensing is the the TOPEX Poseidon is the group of satellites which are used later on, and now is still going to be used for the measurements of the sea level. So we have every 10 days we have the complete picture of the sea level of the ocean with the precision of about, with accuracy of about 1 centimeter. So this is very, very extremely important information, because you will see later how we can get not only the sea level, but we can get also the surface circulation of the ocean thanks to the remote sensing from satellites of sea level. Bathymetry data, we call it. Oh, this is the evolution of some theoretical ideas. I will skip over. And this is how the first measurements in line at the end of the 1872, in 19th century, how the first measurements looked like. So in about 4 years, the single ship has done this trajectory, has done this measurements, in situ measurements. So that means at every single point the ship was stopped and did the measurements of the temperature and salinity at the different points. And you see that there is quite a nice coverage of the world ocean. The only problem is that this measurements, it took like 4 years to do these measurements. So if you want to have the synoptic view, the instantaneous view of what is happening in the ocean, this is certainly not instantaneous, because we are talking about the 4 years. So the difference between measurements here and different measurements there is 4 years. It's not that you can say, okay, these are simultaneous measurements. You have to do very heavy assumptions in order to interpret this as a simultaneous measurements. But these were the technical possibilities at that time. But obviously not only the technical possibilities, but also the idea what to do with these measurements has been evolving, and we're evolving. And now, for example, this is the survey of the National Systematic Survey by the research vessel Meteor, German Meteor expedition, which has done this coverage here. You see all these points? These are the measurements point. These are the points where the ship stopped and did the measurement from the surface to the bottom of temperature and salinity. Obviously, it took like 3 years to do these measurements. But in that case, obviously, the idea, what was behind these kind of measurements, was to study the specificity oceanographic characteristics of the southern Atlantic, because of the number of features which people wanted to understand, like upwelling along the African coast, like the water plume from the Amazon River in the Atlantic, currents which are flowing along the equator, or the currents which are coming from the South Africa into here, the Gacic current, and so forth. So the people, what really they put up a certain number of questions or certain number they just wanted to describe what is happening there, okay? And this is how they did. Another example, always of the in situ measurements, is this one here, then done by the Woods Hole Oceanographic Institution, and with the research vessel Atlantis, and you see what is the technical possibilities to do the much more dense measurements along the much more dense measurements within a shorter period of time. Obviously, Woods Hole is right here, so they were very much interested in this part here. We'll see later why they are concentrated here, because we have here the Gulf Stream. So the Gulf Stream is one of the currents which are transporting the heat from the equator to the polar areas and therefore it's extremely important to understand how it functions, what are the characteristics, what are the features. And so this is the further evolution of our in situ measurements. But these are all done by a single institution or a single nation or a single ship. Obviously, at a certain moment, the people come to the idea that why don't we combine ships with a number of nations and have a better coverage, larger coverage, and a shorter period of time. And this is something which happens during the International Geophysical Year Atlantic Program 57-59, where number of ships of different nations did the number of transects across the Atlantic, both zonal or meridional, in order to understand the entire Atlantic oceanographic conditions at a specific period. And so you can see that that they try to understand the entire thing, and they are also again the rather strong attention paid to the area of the Gulf Stream. So this is the combination of the number of nations and number of national ships in order to do this thing. It was in 57-59 period. There is another international program which is called World Ocean Circulation Experiment, WOS, which combined number of nations, and then they cover the entire world ocean, because we are talking about the World Ocean Circulation Experiment. We would like to understand not only the circulation in the Atlantic, because this has been to a certain extent understood from the previous experiment, but now we extend it to all the oceans. We cover the Atlantic, the Indian, and the Pacific Ocean, and try to find out what are the common features of these three oceans, how we can synthesize the physics or the oceanographic features of the three oceans we are talking about. Some of the measurements were also done in the polar areas in order to understand the circumpolar currents. So this is how the idea evolves, and how, as a consequence of the evolution of these ideas, there is evolution of the measurements, but not only because of the evolution of the ideas, it's also because of the evolution of the technical possibilities. And we are now in era of remote sensing data, and this is the Topex Poseidon tracks. So this is the track in the Pacific during the 10-day repeat of the orbit. So that means every 10 days the satellite covers this with this network covers the Pacific. You see what is the real progress in measuring the oceanographic properties, thanks to the remote sensing, thanks to the satellite, using the satellite data. There is a problem with this, in the sense that there is no problem. This data has some problem in the sense that they give us information only at the surface. We don't know what is happening below. We do know what is the circulation at the surface, but we do not know what is happening below. Therefore, in order to, we cannot really simply rely on the satellite measurements and say, okay, we understand what is happening in the ocean. We should combine the sea surface measurements with the in-situ measurements. Otherwise, we will have only information on the very thin surface layer. If you get the information on the circulation from the satellite data, you get only what is the circulation in the first meter of the ocean. What is happening below, we don't know from this kind of measurements. We do have to have the measurements, oil area measurements with the moorings. We do have to have with floats, with Argo floats, with drifters, in order to get the information on in the water column. But anyhow, the good thing with these kind of measurements is that you have the coverage of the entire ocean, the entire surface in 10-day period, very, very detailed. You do have the very nice horizontal spatial resolution, which is on the order of 10 kilometers. So you have every 10 kilometers, you have the information. So you have a very good temporal and spatial resolution, what we say. Okay, so this is how the idea of the oceanography evolved. Questions? Everything clear? Good. You're better than me. These are the measurements that we can design our measurements in order to respond to a specific question. So we can put the question and then try with the measurements, observations to respond to the question. So the first and the most important aspect of the design of any experiment is to determine why you wish to make a measurement before deciding how you will make the measurements or what you will measure. So you have to decide why do you want to do the measurements? What do you want to measure? What kind of process you want to understand? And then only after that you can decide what kind of instruments, what kind of method you are going to use in order to do these measurements. So the first question is, what is the purpose of our observations? Do we want to test hypotheses or describe the process? Testing hypotheses means that, okay, I say the most important, the circulation in our Gulf here, in the Gulf of Trieste, is the wind-driven circulation. So what do we have to do? We have to do the measurements of the currents, but we have to do the measurements also of the wind. Otherwise, we won't be knowing why there is a circulation here without knowing what's going on in the wind field. This is what but we can hypothesize that since the wind in the Gulf of Trieste is very strong, I suppose, I hypothesize that the wind is the main driving force. Therefore, what I'm going to do, I'm going to measure at a certain number of points the currents and at a certain number of points the wind. Do I have to have the horizontal spatial resolution of the wind and the currents the same? Probably not, because I can suppose that the wind changes on a spatial scale much less than the currents. Okay? Therefore, I might be able to use single point measurements of the wind, or 2, 3, and then larger number of points of measurements of the currents in the ocean. For example, here, if I'm talking of a specific area here. So, you have also to optimize your measurements. It's useless to do the measurements of 100,000 points of the wind, and you know that the wind variability is such that it doesn't change on this small scales. So your hypothesis is also determining the measurement, the type of measurements you do, and also you can optimize your measurements on the basis of the hypotheses. what is accuracy required by the observation? This is what I told you before. If you want to do the measurements of temperature in an area where we know that the variations of temperature on spatial scale is on the order of a degree, I don't have to have the measurements with a precision of with an accuracy of 1/10 of a degree. Obviously, but if I do these measurements in the open ocean, in that case I do need a very high accuracy in order to distinguish between different water masses. This is what I told you before, what the resolution, time and space is required. I have to know what kind of processes I'm addressing in order to decide what kind of resolution in time and space is required. What is the duration of experiment? This is another very important thing. If I'm going to understand or to try to study tides in the ocean, you know that tides have a period of 12 or 24 hours. A major part of these processes are 12 or 24 hours. I cannot do the measurements which are taking place for 5 hours. I wouldn't see any tide, right? I would just see the increasing or decreasing sea level as a part of the tidal forcing. So, but in order to do and to study tides, my experiment duration has to be larger number of tidal cycles. So, more than 10 or 20 or 100 tidal cycles in order to see exactly what are the characteristics of tides. Okay. So the duration is necessarily associated with what we say tidal temporal scale or phenomena. If you want to do the response, if you want to look at the response of the current and the wind, and we know that the wind changes, at least here, on a time scale, a typical time scale of a week or so. In order to understand how the current responds to the wind forcing, we have to have the measurements on the order of months in order to see what is going on in the current as a response to this specific type of wind. Obviously, if you are talking about the areas where the wind is much more steady, like in equatorial areas where we have more steady winds, then we have to have even longer measurements than here. So these are the design of observation experiments, which depends on.
Question?
Yeah.
How can we measure accuracy in our observation?
It depends on the instrument. You know, the instrument has you determine the accuracy and of the instrument. You know, because there are specific techniques to to determine the accuracy of the instrument. You will see later the precision and accuracy of instruments. Here is the definition. Accuracy is the difference between the measured value and the true value. Okay. What? Yes?
If you know the true value, then why do you measure?
Yeah, you do know the true value in a controlled environment. If you have a pool and you control the temperature there, you determine that the temperature in a closed system is 21.15 degrees. This is a true value. You cannot know the true value in the ocean, but starting from accuracy which you determine in the control conditions, then you go with your instruments in the ocean and you know what is the accuracy because you determine your accuracy in a controlled environment. Okay. And precision is the difference among different repeated measurements. So you have accuracy and precision. This is important to see the differences between the two. Okay. Let's see physical settings. So physical settings. In order to understand what kind of environment is the ocean, we have to know some geographic, some geometric characteristics of the world ocean. And this is why I'm calling this chapter physical setting. And what that means? That means that we should know the depth of the world ocean, what are the characteristics of the depth of the world ocean. And so here is the graph which nicely describes the elevation of land and depth of the seafloor. This is the zero. This is the depth of the world ocean, and this is the height, land height. And what is this is the distribution of different depth of the world ocean. What gives you this? What information gives you this curve? This curve gives you that the major part of the world ocean is around 5 kilometers deep. So when we are talking about the ocean, we are really talking about something which is mainly 5 kilometers deep. We have around 5 kilometer thick water in the world ocean, which is quite different with respect to the land, where the major height is around the first 100 meters or something. So this is one important thing, and we will be using this information later on very often and for different purposes. This is the schematic section through the ocean showing principal features of the seafloor. This is our colleague from geology will tell us much more. And so what is the distribution? The distribution we have on the basis of the depth of the ocean, on the basis of the slope of the depth of the ocean, we determine different parts of the world ocean. So if this is the sea level, we have a shelf area. Shelf area is the area which is has a depth less than 200 meters, which is next to the continent, and this is also at the same time characterized by the typical sediments, but at the same time also is characterized by specific circulation, by the fact that there is a freshwater discharge from rivers, so the oceanographic features at the shelves are much different than the open sea. Because if you have the water discharge, then you have the salinity, you will see later, salinity lower than at the open ocean, for example. But then we will see that since the density depends on salinity, we will have that the density at the shelf area is different than the open sea. Then you have the slope area where the depth steeply goes to deeper layers, and here you have also the specific characteristics of the sediments, whereas prevails, for example, mud. Somebody asked something? No. Then you have the central part of the basin. Typically in the ocean you have a mid-ocean ridge, which are the mountains in the ocean, which are sometimes rather high. This is the mainly ridge, but then you have a seamount. Seamount are the isolated mountain at the bottom of the ocean, Then you have trenches. You have the areas, isolated area with very deep part of the ocean, which in some parts is 11 kilometers deep, like a Philippine trench. Then you have the island arcs, islands, and then, so this is the typical characteristics of the bottom of the ocean, and with the typical features which appears there. And you will see that what is important to note here is this thing. Note that the slope of the seafloor is greatly exaggerated in the figure. What is important about this? We said that the ocean is typically 5,005 kilometers deep, but the ocean is at the same time like a 10,000 kilometer large. So if we show in a graph like that, in these proportions, 10,000 kilometers with respect to 5 kilometers, you have a single line. You won't see anything. So what do? We exaggerate the vertical scale in our graphs with respect to the horizontal scale in order to see these features. Otherwise, it will be a single curve and nothing else. So this is why it says here that we exaggerate the vertical scale. We will be exaggerating all the time vertical scales with respect to horizontal scales in order to see the features and the horizontal and vertical distribution of the ocean properties. Here are the description of different features of the bottom. Here, basins are deep depressions, canyons are relatively narrow, deep furrows with steep slopes. Continental shelves are his definition of continental shelf. Continental slopes. Then we have plains, ridges, seamounts, sills, trenches. All these are I show you on a graph, and here is the description in words of this thing. I won't go into details. You just find this here. Let me skip over this, then I'll come back this one. Okay, this is the how it looks like cross section of the South Adriatic along 25 degrees south, showing the continental shelf offshore South America, seamount near 35. Where is the seamount near 35? Should be here. The mid-Atlantic ridge, which is this one here. The narrow continental shelf of South Africa. And here you can see the vertical exaggeration is 180 versus 1. If we take a lower exaggeration, 30 to 1, which is this one here, you don't see practically nothing. If you do the 1 to 1, then you don't see really nothing. But anyhow, you can recognize the features what I was telling you before is as general features of the ocean. You will recognize, for example, in a southern Atlantic, and you can see this is the. Can you imagine this? This is just a cross section at the 25 degrees south, and so you can see that how this looks like and how these in real life look, these features. This is the word bathymetry. I'll be telling you how it has been obtained. But what tells you with the word bathymetry, this reddish means the shallower part of the world ocean, the bluish is the deeper part, and you can see this this mountain chain in the world ocean is really present all over the world ocean. So it's not this scheme is really something which is rather realistically describes what is happening in the world ocean. You have also a number of seamounts. You see, you have the areas of deep ocean areas, and you have the continental shelf. The continental shelf are these reddish area along the continents, which are more or less wide in function whether there is the river discharge bringing sediments or not. For example, see this. There are a number of these shelf areas, but however, the largest number of the world ocean is occupied by the rather deep zone, which is exactly what which reflects the graph what we have seen before, that the major part of the world ocean is like around 5,000 meters, 5 kilometers deep. Just to zoom at a certain part of the world ocean, here you can see the Atlantic, North Atlantic. You can see here how it looks like this mountain chain. You can see the seamounts isolated. You can see a rather large shelf. Here is the Amazon River discharge area. So this is why the shelf is large. Here is also the shelf rather large because of the number of rivers which inflow here. And so you see that the scheme functions rather well.
Please, what do you mean by the shelf?
Excuse me?
The shelf. What do you mean by the shelf? The red color.
Slope.
Oh,
What did you say?
the red colored ones, what do they mean? The red ones near the continents. Like these ones.
Ah, the red one.
Yes,
The red is a continental shelf.
shelf.
Yeah. The red is continental shelf, what we define as an area next to the continent which is shallower than 200 meters.
Oh,
We can zoom in a little bit more. For example, this is a very small area, relatively small area near the California zone, and you can see this is the canyon. You can see this canyon here, starting from the continent. Here is the slope area, and here are a number of canyons. Canyons are rest of the rivers which used to go there. So they left the sign of the flow. The rivers were present at geological times. Okay. The importance of canyon are very large, very strong, and we will see later why. Because they are determining the water exchange between the coastal area and the open sea. Okay? Let's see what are we going to do now. Do we go to do now something? Okay. Now we will be discussing a little bit the heat and water budget. Heat and water budget are important because the ocean accumulates heat and then release the heat into the atmosphere, or the heat is then redistributed within the ocean by ocean currents. So, but what are the components of these heat fluxes in the ocean? And here are the five essentially five important components of the heat budget. The first one is the insolation. QSW is the flux of sunlight into the sea. So the sun is radiating the heat into the ocean absorbs this heat and accumulates it in this. Then we have a net infrared radiation, net flux of infrared radiation from the sea. Infrared radiation is the radiation of the heat, which is simply due to the temperature of the ocean. The higher is the temperature, higher is the infrared radiation. This is the where the ocean behaves as a black body. This is a black body radiation, where the ocean release the heat due to the fact that it has a certain temperature. Then we have a sensible heat flux. Sensible heat flux is the heat flux between the ocean and the atmosphere due to the simple fact that the two of them are in contact and they have a different temperature. So the sensible heat flux essentially is due to the different temperature between the ocean and atmosphere, or the temperature difference between the ocean and atmosphere. Then we have a latent heat flux, which is the flux of heat carried by evaporated water, because obviously at any single moment the ocean evaporates into the atmosphere, the water evaporates from the ocean into the atmospheres due to for example, due to the wind. The wind is helping the evaporation from the sea surface. And then finally, number 5 is the advection of heat carried away by currents. If you look at these 5 elements of the heat flux, the difference between number 5, advection of heat, with respect to other 4, is that the advection is not looking from the point of view of the entire ocean. Advection doesn't change the heat content in the ocean. It changes the heat content in different parts of the ocean because it brings the heat from here to there. But the other 4 components, insolation, net infrared, sensible, and latent, they are changing the heat content in the entire ocean. If you do the integral over the entire ocean, you will see that due to, for example, the insolation, the heat content over the entire ocean will change. But if you do the integral of the heat and find out what is the contribution over the entire ocean, find out what the contribution of the advection, you won't find anything, 0. Because the advection is simply responsible for redistribution of the heat and not on the... And finally, what this conservation of heat requires is that the sum of these 5 components gives us 0. Why it has to give us 0 over the entire ocean? Do you know why? If you do the integral over the time of this total heat, it has to be 0 because the ocean is not heating or cooling in the time scale, a certain time scale, right? Unless we do have some climate changes, what we are facing now. In that case, yes. In that case, the ocean is on long-term time scale is heating. So this conservation of heat is not necessarily 0 on a long time scale if we are facing the climate change problem. Okay. Otherwise, with this integrated over time and integrated over the entire world ocean has to be 0. Okay. So this is the sum of heat fluxes. And here is what is happening with this energy which comes from the sun as a function of wavelength. How the spectrum of the solar energy as a function of wavelength looks like at above the atmosphere. This is one thing. This is the continuous line. The dashed line is the black body radiation at the temperature of 5,900 Kelvin. So you can see that the sun is radiating in energy more or less like a black body at the temperature of 5,900 Kelvin. Once the solar radiation reaches the surface of the Earth, which is this curve here, you can see that it changes the shape. It has some wavelength where the energy has been absorbed much stronger than the rest of it. And in general, the whole curve is put down, so the part of the energy has been absorbed by what? By atmosphere, because the difference, this is above the atmosphere, and here is at a 2 meter surface in the Earth. So the difference between these two is the energy absorbed by the atmosphere. Therefore, atmosphere absorbs part of this energy coming from the sun. The rest is then absorbed by the land, absorbed by the sea, by the ocean, and this is how it looks like.
Question.
Yeah.
So if you look at the peak of the graph, you realize that the solar radiation, the spectrum at the top of the atmosphere is higher than that of the black body radiation. Why is it the case?
What? Say, please.
At the peak, the top.
Yeah.
Yes. The spectrum there is peaking higher at the top of the atmosphere.
With respect to black body radiation. But you know, black body radiation is the theoretical formula, which is this formula, temperature proportional to temperature to the fifth, if I'm not wrong, right? So this is a theoretical curve of the black body radiation. Obviously, the sun is not a black body, completely perfect black body. Sun is, in the first approximation, or a black body with a temperature of 5,900 Kelvin. But obviously, you see that there are a number of parts which where the radiation, solar radiation, is smaller than the black body. Some parts where it's higher, like here, or here is smaller, here is higher. So you know, it depends. This is the difference between theory and experiment. Okay. Okay. Let's see, what is this? Wow, I don't want to shift it. These are all different These are different parameters which are used to determine different components of the heat flux. I won't go into these details. Don't worry. But what is the all these coefficients, by the way, are experimentally determined, and they are used to calculate all different components of the heat flux. Therefore, they are very important, but I don't want to go into details because otherwise you will fall asleep. Which is important is this schematic diagram, which shows how what is the percentage or what is the amount of energy, solar energy, which is absorbed by different components of the Earth, by atmosphere, by the ocean, by the land. What is the importance of evaporation, evapotranspiration, transpiration, and so forth. Okay, so first let's see the incoming solar radiation is like 342 watts per meter square. This, if you make the integral over this curve, what I have shown you before, as a function of wavelength, you will get like 342 watts per meter square. This is the annual mean. Okay, obviously it changes on an interannual scale because the intensity of sun radiation changes in function of the radiation of the state of the sun. Then from here it comes only 168, so like almost half reaches the sea surface, reaches the ocean or the land, and the rest is absorbed by the atmosphere, reflected by clouds. There is also reflection, it's not only absorption. Absorbed by the atmosphere, reflected by sea surface, and then only half of that is absorbed by surface, land or the sea. And then we have evapotranspiration, which is at the land. We have the surface radiation here, which is important, which is surface radiation, so the radiation of the sea surface as if the sea surface behaves as a black body. Okay, as the same thing as the sun was behaving very similar to black body at the temperature of 5900 Kelvin. The same thing happens with the sea surface, which behaves as a black body but a different Kelvin different temperature. So it goes into the surface radiation, which goes back. There is also at the same time there is a back radiation, because when one part of the energy is radiated into the atmosphere, which is accumulated from the sun, in the atmosphere we have what we call greenhouse gases. You have heard for greenhouse gases. Part of this energy they absorb, and what they do, they really do that the energy which is radiated from the Earth does not get lost into the space, but it's kept in the atmosphere. This is thanks to this fact, thanks to green gases, the atmosphere. And the atmosphere is like the average atmosphere temperature is 15 degrees. Otherwise it will be -10 without greenhouse gases. So these greenhouse gases have a very important role. We have heard about greenhouse gases a lot in terms of the climate change. We have heard of greenhouse gases as anthropogenically produced greenhouse gases, but they are naturally present in the atmosphere also. the climate change has been generated by greenhouse gases, not because they are naturally present, but because the man, are producing additional quantities of greenhouse gases, which are due to this absorption by these greenhouse gases causes the increase of the temperature in the atmosphere. This is how and why we have the climate change, because there are an increase of the presence of the increase of greenhouse gases in the atmosphere, which then increases the absorption of the backward radiation in the atmosphere, and then generates the increase of the temperature of the atmosphere and the land. Okay? This is important to remember. And obviously there is also the part of the energy which is absorbed by the atmosphere is emitted into space, because also the atmosphere behaves as a black body, and on its turn radiates the atmosphere, the heat into the space. So this is how it looks like graph. This looks rather complicated, but it's not so complicated, and it gives you an idea what is the percentage and how this energy, which is essentially coming from the sun, is distributing within the atmosphere, ocean, land, and so forth. Okay? Questions? Let's see, what is this? Yeah, this is what we know, that the main source of the heat in the ocean or the earth in generally is the sun. Obviously, the position of the sun is a function of the latitude. So the lower is the latitude, the higher is the energy coming to the sun, to the earth. Therefore, this is the heat flux component due to the sun, QSV. Solar the heat transfer to the ocean by solar isolation is this one here. You see that there shows a maximum around the equator. There are this minimum, local minimum here around the equator, but this is due to the increase of clouds in the equator. It's a subtropical area where you have a lot of rain. Okay, you know probably better than me. So you see that that you have a large quantity of heat transferred to the ocean around the equator and from mid-latitudes north to the south. Then what we have here, Q latent heat, L latent heat flux is this one here, which shows practically the intensity of evaporation. Intensity of evaporation, which is largest around in subtropical areas, and with the minimum around the equator. And then we have sensible heat, and we have finally loss by long wave radiation, which is this thing here. The sum of these three should be zero if we do the integral over the entire ocean. But we have to take into consideration the transport. Because the transport is something which keeps, which tries to take the heat from the equator toward the polar areas, from one side to the other side, so forth. Okay, and net heat flux through the sea surface calculated from the data above, this is the solid line, and net heat flux constrained to give heat and fresh water transport by the ocean that match independent calculations of these transport. The area under lower current ought to be 0, but it is plus 16 watts per meter square for the unconstrained cases, -3 for the constrained case. So some of these things gives you this continuous line as a total heat flux. So you can see that the heat flux components very nicely reflects its function of latitudes, and this obviously, you know how we obtain these curves. We did the integral over the longitude, so it's like we integrate all over the Earth in order to get the total heat flux components. Okay, so I think we.
So why is the long wave minimum at the equator when it is maximum in terms of the